welcome. So we're going to continue on with monotonicity. So when a derivative is equal to 0, this is where maximum and minimums occur. But not all times that our derivative equals 0 do we necessarily have a max or minimum. So here we're going to look at 4 cases where the derivative is 0, right? And it's where x is c. And we're going to take a look at how these are each different. So let's look at the first one. Right? So let me just notate here that our derivative at c equals 0. So now let's take a look at either side of our function here. Of course, the derivative is 0, right? Because we have a horizontal tangent line, right? So for values that are less than c, right? So here x is less than c. Let's take a look at our derivative. So our derivative is going to be, because our function is increasing, our derivative is greater than 0. Right? So function's increasing. Let's look for values of x that are greater than c. All right? So now our function is decreasing. Right? So our derivative here is going to be negative. We can see on our graph, as well as from the derivative, that here c is a relative minimum. Excuse me, c is a relative maximum. I don't know why I said minimum. Relative maximum. Maybe I'm thinking ahead to the next problem. So c is a relative maximum. All right, so now let's look at the next example. All right, so again, here's our derivative. Excuse me, here's c, and our derivative at c is again 0. Right? Again, we have a horizontal tangent line. All right, so let's look to values for x that are less than c and x that is greater than c. All right, so for values of x that are less than c, our function is decreasing. Right? That didn't come out looking very nice. When I can't see my words when I'm writing, sometimes I can't tell. All right, there we go. So we're decreasing, which means that the derivative is going to be negative. For values of x greater than c, right, our function is increasing. Let's see if I can make that fit in here. Okay. And our derivative is positive. Right? So our derivative is changing from negative to positive, and we could tell from the derivative as well as from our graph that here c is going to be a relative minimum. All right, let's continue on. By luck, they're probably all attached. All right, so here we have c again. All right, so again, we have a horizontal tangent. Can't argue that. It's a horizontal line. All right, so again, our derivative at c is 0. All right, so now let's look to the for values of x less than c and values of x greater x less than c. The derivative is 0. And for values of x greater than c, the derivative is 0. All right, so there's no change to the derivative for values less than or greater than our value of c here. So that means c is not a relative max or minimum. So c is neither. Right? Not a max, not a min. All right, let's look at our last example here. We do have a horizontal tangent line. All right, so notice we kind of have this sort of leveling here. All right, and so f, I'll put it right up here, f prime of c is 0. Let's look at values on either side. All right, so here we're going to look at c less than 0, x less than c. That's what I meant, right? X less than c. And then we'll look for values of x that are greater than c. And I'm kind of hard stretching to write here. My microphone cord is sort of stuck, and I'm afraid if I pull too hard, I'm going to knock out the other cords. All right, so let's look at our derivative. All right, so for x values that are less than c, all right, so you see our function is decreasing. All right, so that means that the derivative for values of x less than c is negative. Now for values of x greater than c, our function is still decreasing, which means that the derivative is still negative. There was no change in the derivative. So when there's no change, we just keep decreasing. Right? That's not a relative max. That's not a relative min. You can see that from the graph. This is neither. So C here is neither. So not all the points are maximum and maximums or minimums. Right? To help us figure out whether a value is going to be a maximum or a minimum, because we're not necessarily going to have a graph here, we're going to have an equation, a function. How we can tell if our points are maximums or minimums is by using a sign chart to help us analyze the derivative. All right, and so how we can use the derivative to tell whether it is a maximum or minimum or not. All right, so what we're looking for are changes in sign. So if f prime of x changes sign from positive to negative, then that value of x, it's a relative maximum. And if f prime of x changes sign from negative to positive, then x is a relative minimum. Right? If there's no sign change, at x for f prime of x, all right, then x is neither. Right? It's neither going to be it's not a relative maximum and it's not a relative minimum. Right? So that's how we can use our sign chart to help us. All right, and we're going to look at several problems using a sign chart to figure out whether the derivative is a relative maximum or relative minimum at critical values. All right, let's continue on. All right, so without a graph, we must find critical values and discontinuities and then test the intervals in between them. Now, we got a vocabulary word here. So write this in your notes. What are critical values? All right, so critical values are where f prime of x equals 0 or where f prime of x is undefined. All right, those are our critical values. We're going to look for both. All right, is our derivative 0? Is our derivative undefined? All right, that's the only place that our function can have relative maximums and minimums. All right, so we want to find the open intervals on which f of x equals x cubed minus 3 halves x squared is increasing or decreasing. All right, so let's go through the steps. All right, so our first step is to take the derivative. I forget which ones are in your notes because your notes aren't in front of me, but write down anything I write if the problem's in your notes. All right, so because you'll have other opportunities to write if this one's not. So you're going to take the derivative. So the derivative of f of x, where's my prime? There we go, is equal to, so the derivative of x cubed is 3x squared. Derivative of, I'll have a negative there, 3 halves x squared. All right, so I'm going to be multiplying by 2, right? So I'm going to have 3 halves times 2. So that's just going to be negative 3 because the 2's will cancel. Right? And then we'll have x to the first power, right? Because we reduce that exponent by 1. All right, so that's our derivative. Step 2, set the derivative equal to 0. All right, so we have 0 equals 3x squared minus 3x. It's an easy factor. Just factor out your greatest common factor here, which is a 3x, and you're going to have an x minus 1. All right, so we have 2 critical points. We have, so far, we have 3x equals 0, and so x is 0. And we have x minus 1 equal to 0, so x is 1. All right, so these are our critical points. All right, the only other place we can have critical points are when the derivative is equal to 0. All right, so we should always just make sure, we're going to check if f prime of x is undefined. All right? All right, so check if it's undefined anywhere, or you can think of it as check if the derivative is defined. Right? So if it's defined, it doesn't have any critical points here. If it's any places where our derivative is undefined, then we'll have critical points. All right, is our derivative ever undefined? Well, no, this is not applicable, right? Because polynomial functions are differentiable everywhere. And it may not seem like an important step, but it really is, because if your derivative is not defined somewhere and you forget all about that point might be really important. All right. So we're looking for check to see if the derivative is undefined anywhere, or let me add that. Actually, let me write this as a nicer sentence. Whoop. So I want to add one more thing to that, and I want to add at the beginning. So the 2 things that we're checking for any discontinuities. Oops, because if we had a discontinuity, then our function wouldn't be defined. Our derivative wouldn't be defined there. So check for any discontinuities. Or values where the derivative is undefined. Want to put the discontinuities first, because you may notice those before you would notice the derivative being undefined. And again, this is still an A, right? Because polynomial functions are continuous and everywhere differentiable. Polynomial escape solvable there. Polynomial functions are continuous and everywhere differentiable. Because you can be continuous but not be differentiable everywhere. For instance, absolute value functions. Right? They're not differentiable at their vertex because it's a corner. All right, so now we want to create our sign chart. I think I'll do that up here. All right, so we have 2 critical points. We have the 0 and the 1. All right, you want to put those, you want to make sure you put those critical points in order from least to greatest, and then you're going to evaluate for values on either side. Right? So I'm going to write this in red. So list critical points. Oh, that doesn't look very. That's like a Q. List critical points in order from least to greatest, and evaluate for values on either side of the critical points. Okay? All right, so we've got 0 and 1. This is where our derivative was 0. All right, so we need a value less than 0. How about -1? We need a value between 0 and 1. I guess that's going to have to be 1/2. And then we need a value greater than 1, and that's 2. And you don't care what the value of the function exactly is. You just care, is it positive or negative, all right? And, excuse me, I say function, you don't care what the value of the derivative exactly is. You just care if it's positive or negative, because we're evaluating in the derivative. Maybe I should put that over here so you know that I'm talking about the derivative. And you remember that. So we want to evaluate f prime of x for values on either side. All right, so we're plugging into this right here. All right, so if I plug -1 into 3x, that's going to be negative, right? This would be negative. If I plug in -1 into x minus 1, that would be -2, and that would be negative. And if I multiply two negative numbers together, that's going to be positive. If I plug 1/2 into 3x, that's going to be positive. If I plug 1/2 into x minus 1, it'll be negative because it'd be -1/2. So that's going to be negative. If I plug in 2 into 3x, that would be +6. If I plug 2 into x minus 1, that is a +1. That is positive. All right? So we've got our sign chart there. I'm going to move these lines out of the way, and pluses and minuses. We don't need them there anymore. All right? So you don't have to calculate out what the value exactly is. You just need to know whether it's positive or negative. All right? And so now we can answer the question. I think we've got everyone there. All right, we need to interpret our sign chart. All right, I guess I'll switch colors again. I'll go to blue. Now, I write way too big. That's what I have discovered. So we're going to put it right here. So we're going to evaluate. That's our last step. All right, because your sign chart is not enough. All right, you need to interpret. Excuse me, not evaluate, interpret. Interpret our sign chart. We already did the evaluating. Right, so interpret sign chart. All right, so we're asked, where is it increasing or decreasing? All right, so since f prime of x is greater than 0, for values, and I'm just going to put for values that are less than 0, and it's fine to use symbols, and greater than 1, f of x is increasing. And actually, let me put x less than 0. That looks a little bit better. And x greater than 1. F of x is increasing on the interval -infinity to 0 and 1 to infinity. I'm going to move this down a little bit. If I hadn't written across so much and written down a little bit more. I gotta squeeze the last little part in. Oops. Well, most of it moved down. Come on. Everybody move down. Move down. All right, move you down. There. Go back. Oh, I hate when that happens. And I don't even know how it happens. And I don't know how to undo it. Other than maybe hitting undo. There. You come down. You come down. There. The poor people, they're just watching me move things. There. And you're all being obstinate, all you little words. There we go. This is the big part here, the finish. All right, and since f prime of x is less than 0, for x, I'm going to write this a little bit farther this way. For x, and it's x between 0 and 1, so we can write it like that. Oops. Don't write it like that. Like that. In the right order for the numbers. So since f prime of x is less than 0, for x between 0 and 1, f of x is decreasing on, I'm going to leave the word interval off and just put 0 to 1. And there we go. All right, that's a complete answer. All right. Now you don't need to necessarily take the derivative and when you're solving this out, or set the derivative equal to 0, or check for any discontinuities, etc. But you do need to have your derivative. You do need to set it equal to 0. You do need to have a sign chart, and you do need to interpret it. Now you do need to check, right? And if you find any, you need to write those down, if those are critical points. But you don't need to write the words. Check. Right? This is for our notes, right? And this is to remind you of the steps. All right, let's do another one. Let's see if I can do it a little faster. And, on my writing. Find the open intervals on which f of x is equal to 3x to the fourth minus 4x cubed minus 2x squared plus 5. We want to know where it's increasing or decreasing. Step 1, take the derivative. So I'm going to try to go faster. Now that I did the steps. Good enough. I can always fix the handwriting later. Oh, perfectionist me. Derivative. It would help if I could see my writing when it comes up. All right, our derivative, f prime of x, is 12x cubed minus 12x squared minus 24x. Of course, the derivative of 5 is 0. All right, so now step 2. Set derivative equal to 0 and solve. All right, so we've got 0 equals 12x cubed minus 12x squared minus 24x. We can factor out a 12x. So we've got x squared minus x minus 2, and that will factor to 1. All right, so we have 3 critical points. 12x equals 0, and then if we divide 12x by 12, oops, I wrote 12x, that's okay. Get rid of this one. All right, so 12x is equal to 0, x is 0. The slowness of the board sometimes just kills me. Move over. All right, just stay where you are then. Who cares? All right, x minus 2 equals 0. So x is 2. X plus 1 equals 0. X is negative 1. We're not even going to wait for these words to come up. All right, so now we want to check to see if check that the derivative is defined everywhere. Come on. Holy cow. Come on. The rest of my 1. How about the rest of my 0 too? All right, so check the derivative is defined everywhere. I'm going to write it shorter. So I wrote the whole thing on the last slide. All right, so, and this is NA. Polynomial functions are continuous everywhere. If you were asked if it was undefined, you know, or why there are no undefined, this would be your justification. Polynomial functions are continuous and differentiable everywhere. There, now I managed not to take up so much space. Step 4, sign chart. Right, again, we've got to list them in order from least to greatest, and we'll check the values. In the derivative. All right, so we've got -1 is the smallest, and then 0, and then 2. So we can plug in a -2, and that one's a 0, that's a 0, that's a 0, a -1/2, and a 1. All right, so if I plug in a -2 into 12x, that's going to be negative. If I plug in a -2, I'll have negative plus a negative, that's going to be negative. And if I plug in a negative here, -2 plus 1 is negative. 3 negatives, that's negative. If I plug in -1/2, that one, 12x will still be negative. X minus 2 will still be negative, but this one will be positive. All right, so that will make this positive. If we plug in 1, this will be positive. X minus 2 will be negative, and x plus 1 will be positive. All right, so that will be negative. All right, so now we've got our sign chart. All right, so now we can evaluate. And I really kind of like to move these things back out again because we don't, they look weird there now. We're done with them. Last one, okay. All right, so let's evaluate, and that's the end of this problem. All right, so let's interpret, not evaluate. Interpret. Let's interpret the sign chart. So always got to interpret your sign chart. All right, so we're looking. There we go. F prime of x. I'm going to write it as negative, so I don't have so many less thans. Is negative, but writing, you know, a less than symbol with a 0 or is negative is the same thing. So since f prime of x is negative, from -2 from -2 to, excuse me, let me write that better. So is negative for values, there we go, get my train of thought back, for values less than, I'll write values of x, less than -1, and x, and we want x in between, so I'm going to put that x in between. Okay, so right here for values less than -1, we're negative, and then also values that are in between these two, right? All right, so and so for x values that are between 0 and 2. All right, so since our derivative is negative on those two intervals, f of x is decreasing. On the interval -infinity to -1 and 0 to 2. Right? And then because f prime of x is positive, and it's only positive, oh, we forgot to evaluate one place. Bad me. I didn't put the value on that side. All right, if we plug in a 3, it's going to be positive, 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 right? You're going to have a 36, you're going to have a 1, and you're going to have a 4. All right, so because f prime of x is positive for values, and so that's in between negative 1 and 0. I'm going to write values of x, and then this just means such that. I like to use different vocabulary sometimes. All right, and so we're between negative 1 and 0, and x greater than 2, f of x is increasing on negative 1 to 0 and 2 to infinity. There we go. All right, so there's our justification. So there's a couple different ways you could write it, right? You just need to make sure that you properly notate things. All right. All right, so let's continue on. I think we can do one more. I don't want to go too much longer, but this is almost finished actually. All right, so for continuous function, knowing where and when and where the sign of the derivative changes lends great insight into the existence of any relative maximums or relative minimums. All right, so the first derivative test for relative extrema lets x equals c be a critical value of a continuous function f. If f prime of x changes from negative to positive at x equals c, then f has a relative minimum at x equals c. All right? And that is located at c, f of c, right? Because we'd have to plug back into the original function. All right, so yeah, if you go from negative to positive, there's a relative minimum, and I have a little picture there you can add to your notes. If f prime of x changes from positive to negative at x equals c, then f has a relative maximum at x equals c. Right, and the exact location would be c, f of c, right? Because we plug back into the original function. If f prime of c is positive on both sides of x equals c, or negative on both sides of x equals c, then f of c is neither a relative maximum nor a relative minimum. There has to be a change in sign. All right, so here's your visualization. All right, so here in the first example, right, on A we have a local maximum, right, because f prime of x changes from positive to negative. And there's some tangent lines in here, right, to show you that the slope of the tangent line is changing. Right, and then over here, f prime of x is less than 0 for values of x less than c. F prime of x is greater than 0 for values of x greater than c. All right, so we have a local minimum there at c. All right, here we have for values of x less than c, our derivative is positive. For values of x greater than c, our derivative is still positive. All right, so that is not a minimum or a maximum. And same thing over here. All right, so for values of c less than 0, our derivative is negative. F prime of x is negative. For values of x greater than c, our derivative is still negative. That's not a maximum or minimum, right? Because there's no change in sign. So when using the first derivative test to justify relative extreme, you must write a concluding statement clearly communicating the type of sign change of f prime at each x equals c. All right? Thou mustn't use pronouns either. Why must you not use pronouns? It is increasing. Is not what is increasing. Is it what is greater than 0? Okay, so you can't say it's greater than 0. What are you talking about? Is it f of x you're talking about? Is it f prime of x? Nobody will know. All right, so if you're talking about f prime, you write f prime, right? If you're talking about the derivative, write it. If you're talking about your f of x, your original function, from which you got the derivative, then write f of x. All right, so no pronouns. They're too vague. All right. I think there's only a couple more left. We have 1, we have 2, 3, 4, I think there's 5. All right, so I think I'm going to stop this podcast so the video doesn't get too long, and I'll finish up on the next video. Bye for now.